All right, guys, welcome back. So last time we talked about k-means clustering algorithm, and then we went into the discussion of hierarchical clustering algorithm. So um, just as a recap, the hierarchical clustering is basically about clustering the data from a bottom-up sense, where you first begin with a sort of a distance matrix showing the distance between the data set, individual data points. So let's say you have data points like this, and what you do is to compare the distance among the data points that you have, and then start merging the pairs that has the smallest distance. And then by doing that, we've seen last time that we could construct a graph that looks like this, where the height of the graph represent the similarity between the 2 points, and then the connection is basically indicative of the hierarchical structure among the data set. So this kind of a graph was called a dendrogram, if you recall. So we're going to build upon that, and then we're going to talk about how actually that computation could happen, and then we'll move on to the issues regarding clustering in big data scenario. So the basic agglomerative hierarchical clustering algorithm begins with computing the distance matrix between all data points. So for all pairs, you construct a distance matrix showing the pairwise distance among all points. And then basically, in the pseudocode, it's pretty simple. So you just merge the two closest pairs. So by searching through the distance matrix, and note that the distance matrix is symmetric, so you don't really have to search the entire matrix. You can just search for the either upper triangle or the lower triangle. But anyways, you search through these distance matrix, and then find an element that has the closest the smallest number, and that's the pair that has the closest distance. So let's say that's the ith row and the jth column. And what that means is basically you need to merge the ith data point and the jth data point and then build a cluster. Okay, and then after that, since now we have merged the ith component and the jth component, we need to somehow update the distance matrix. Obviously, the data point I and the data point j has been merged together. So now, the 2 points that were previously separate columns now needs to be merged into one column, right? So you need to basically recompute the distance matrix, and then basically repeat this 2 steps until you have no other pairs to merge, right? So that's basic algorithm for hierarchical clustering. Now the question is, how to, for selecting the pairs with the smallest distance, it's a simple search problem. So you need to just go through the all the entries of the distance matrix. But in terms of the distance matrix calculation, you probably don't want to update the entire distance matrix each time you merge the 2 data points. Instead, somehow you probably want to utilize the existing distance matrix in order to minimize the computation, because as you know, we've seen a couple lectures ago, computing the distance matrix in a naive manner is taking really long. Even for like 4,000 rows that we used in our toy example, it took 2 minutes or 3 minutes to compute the distance matrix. So if you think about a situation where there are more zeros to the number of data samples n, it's going to be nearly impractical to compute the distance matrix each time for every iteration. So the idea behind that is as follows. So in fact, you don't really need to compute the distance matrix from scratch. Of course, at the beginning of the iteration, you probably want to compute the distance matrix. So what's going to happen is, well, first of all, let's say you construct a distance matrix, okay? And then let's say this element, okay, turns out to be the smallest distance or the highest proximity, right? And in that case, what needs to happen is P1 and P2 needs to be merged, right, as a result of that. Now, if you think about it, these two rows and these two columns needs to be merged together. Does it make sense? To form a new row and a new column that corresponds to the cluster that is formed by P1 and P2. So, and then if you look at the, other locations in the distance matrix, you probably realize that you don't really need to update the distance matrix for that portion, because, like for example, this one over here is still the distance between P4 and P5, and then merging P1 and P2 into a cluster doesn't really make any influence to the distance between P4 and P5. So perhaps at the beginning, when you create the distance matrix and initialize it, at the very beginning, you probably want to compute the distance matrix, as precise as possible. So, you could use a Nystrom approximation or other approximation method, but at the end of the day, you will need to compute the distance matrix for the entire entry. But then, each time for every iteration, when you update by merging the rows and columns, you probably don't want to do everything from scratch, but rather want to keep the result of the previous computation as much as possible, so that we don't have to spend more computation for updating the distance matrix. So that's the key idea. Now let me kind of show you how this thing actually works with more solid examples. So let's say this is kind of the current state. So without losing the generality, at some let's say kth iteration, this is kind of the current state of clustering. And then what we plan to do is to define the operation for a generic kth iteration. We're gonna induce that for the other generic situation. So we're not going to assume anything. We're gonna just look into some generic scenario where we're in the middle of kth iteration. And let's say in the proximity matrix, sorry, the distance matrix, let's say for example C2 and C5 turns out to be the closest closest pair in the current state. Okay, so C2 represents either a single data point or a cluster of data points. Same thing with C5. It can either represent a single data point or a cluster of multiple data points. So we're, like I said, assuming a generic scenario. Now, let's say C2 and C5 turns out to be the closest pair. So in other words, this element over here turns out to be the one that has the smallest value in the distance matrix. Now, what we're going to do is then to merge the C2 column with the C5 column. And then similarly, we're going to merge the C2 row with the C5 row. Okay. Now, in doing that, the idea is, well, simply by using the values that we previously had in C2 column and the C5 column, we can actually merge the two columns fairly easily without actually having to compute the distance again. So regarding that, we need to actually define a strategy to measure the distance between two clusters. So for 2 points, we've talked about distance functions, right? And then once you have determined the distance function, then the distance between two individual data points, the distance computation becomes straightforward. But then let's say you have a cluster of data points. Now the question is, how can you define the distance between the two clusters? So regarding that, there are actually a couple of different strategies. So the first of all, the first thing I'm going to introduce is what is called a single link distance. So the single link distance is defined to be the minimum distance, okay, between the two clusters. So what this equation explained to us is that, let's say you have a cluster CI and then a cluster CJ. And then by using the elements of CI and the elements of CJ, you can define distances. And let's say X is an element that is selected from CI. Okay, X is an element in CI, and Y is the element in CJ. Now let's consider all possible combinations, okay, of x, x and y. Okay. Now, among all possible, pairs between Ci and Cj, what single link distance pursues is to find the one that has the smallest distance value. So in this, diagram, probably these two pairs is going to have the smallest distance, right? So this x over here and this y over here are the ones that probably creates the smallest distance, right? And that's basically the going to be the definition of the distance between the two cluster in the single link distance sense. Okay, so that is called a single link distance. Now, getting back to this issue of updating the distance matrix, here's an example. So let's say here we have, well, in this example, we have a proximity matrix. The reason I can know that is, the diagonal components are ones, okay? So as opposed to zeros. So we know that this is the proximity matrix. So in this case, we're not finding the minimal value, we're finding the maximum value, okay, from the upper triangle. So if you look at the upper triangle of this matrix, obviously the largest proximity is 0.9, which means data point 1 and data point 2 needs to be merged into a cluster. Okay. Now, what I'm going to do then is to to try to merge the first column and the second column. Okay. And when I do that, here's the important trick. Under the single link distance, we're selecting the distance that has the minimal distance between the two clusters, which means the highest proximity. So by merging, let's say data sample 1 and data sample 2, we're going to form a cluster C. Okay, and then the 0.3, 0.4, 0.5 is going to stay there. Now the single link distance, we're trying to find the one that is closest. So with respect to the data sample 3, data number 3, you compare the distance between 1 and 3 and 2 and 3, and then we're going to select the one that has the smallest distance or the highest distance in case of proximity. Highest value in case of proximity. We're going to do the same thing. So for, let's say, data point 5, we're going to compare the distance between 1 and 5, and then the distance between 2 and 5, and then we're going to select the one that has the highest proximity. So as a matter of fact, the first and the second column over here is a matrix that shows the distance from the data point 1 and data point 2 to data point 3, data point 4, and data point 5. Okay, which means from the cluster of 1 and 2, okay, from the cluster of 1 and 2, for example, 2 and 3 has the higher proximity than 1 and 3, right? And 1 and 4 has the higher proximity than 2 and 4. And then similarly, 2 and 5 has the higher proximity than 1 and 5. And what we're going to do is when we merge these two columns together, we're going to select simply the value that has a higher number, okay, among these two columns. So the ones that I highlighted with the orange color, orange boxes, are the one that has a higher value. And when we merge them, we're going to keep this 3x3 component over here that has nothing to do with the first column, the first data point and the second data point. So we're going to keep that as is, like this. And then when we merge the first two columns, we're going to select the one that has a higher value, like this. Okay. Similarly, this is a proximity matrix, which means it's got to be symmetric. So I don't even need to compute anything. I'm just going to copy this value over here, copy this value over here, and then copy this value over here. And then we all know that the diagonal component is always going to be 1. So this is in fact the distance matrix, the proximity matrix after merging the first and the second element in our data sample. So now the distance matrix has been updated like this, okay? And then again, we're going to repeat the same procedure. We're going to take a look at the upper triangle, and then we're going to find the one that has the largest value, because this is a proximity matrix. And then from this, what we're going to do is then to, this indicates that the fourth data point and the fifth data point has the, highest proximity. So they're going to be the ones that's going to be merged. And from this, we do the same thing. We basically compare these two columns. And then, you don't have to worry about this this block over here, because that's going to be merged into, one, since we're on the diagonal. Now, on the fourth column and the fifth column, we're going to select the ones that has a larger value, which in this case, 0.65 and 0.40. And that's going to be, our distance matrix, sorry, the proximity matrix after merging the data point 4 and data point 5, okay? Again, we repeat the same thing. On the upper triangle, we find the one that has the largest value, which is 0.7 over here. And then based on that, we know that, this cluster, the cluster formed by 0.1 and 0.2, has the closest proximity with the 0.3. So those are going to be the ones that are going to be merged. And then if you look at, the distance matrix over here, this whole 2x2 section, 2x2 block is going to be merged into one. And then for the rest, we just need to find the one that has the largest value. And as a result of that, this is the distance matrix after we do the computation. At this point, we don't even need to do any further computation, because now we have a cluster of 1, 2, and 3, and then we have a cluster of 4 and 5. So, the next step is obviously to just merge them together, because we have only two clusters. So that's going to be what's going to happen next, and 0.65 is going to be the value of where this dendrogram is getting connected between cluster of 1, 2, and 3 and cluster of 4 and 5. Okay, so that's basically how hierarchical clustering works. So in fact, merging of the pairs is a simple process. We don't really do any distance computation. We just recycle the distance matrix that we created at the beginning. And then the later process is basically to find the largest element in the proximity matrix on the upper triangle. And then, using that information to merge two columns. And then when we merge the two columns, basically we're just selecting the highest value for the single link clustering. Okay. So one thing to notice here is that the majority of the computational load, okay, is going to be applied at the beginning of the algorithm. At the beginning of the algorithm, where we actually have to compute the distance matrix. Another thing is when you have to go from iteration number 1 to whatever number of iteration you would require to merge all the data points, right? At the beginning, we're going to have a larger computational time per iteration. But as we get closer to the end, the computational time for each iteration is going to be reduced. So it's kind of an unbalanced algorithm where the majority of the computational time is kind of concentrated at the beginning of the algorithm, and then the later process is actually fairly simple. So that's the analysis of hierarchical clustering from the computational time perspective. Now, from the distance metric perspective, there are certain things we need to talk about the single link clustering. So obviously, the reason why people are using single link clustering is because it is easier to compute. In terms of merging the distance matrix, you just need to find the one that has the highest proximity or the smallest distance, right? Now, geometrically speaking, single link clustering method can handle non-elliptical shapes very well. So being elliptical means, the distribution of a cluster kind of follows a distribution similar to Gaussian distribution, right? And having non-elliptical shapes means you have a distribution that is quite far from a Gaussian, a nice, pretty Gaussian distribution, right? So for example, when you have two clusters that are not so balanced, okay, in case of k-means clustering, you may end up clustering these points into two like this with this awkward line in the middle as a boundary. But in case of single link clustering, since we're comparing the distance between the cluster using the shortest distance, after the convergence, we can correctly identify the the appropriate boundary between the two clusters. So when the clusters are not so well balanced, then the single link clustering is the way to go, because it provides a better kind of a distinction, between the cluster with respect to kind of the margin between the cluster. Okay. Now, the limitation of single link clustering is that when you have a noise, okay, and when you don't have a clear distinction between two clusters, so this is almost identical distribution than the previous case, except that we have some outliers in the middle between the two clusters. And the slight difference like this can cause a significant difference, after the clustering, because then the noisy values are going to kind of mess up, in terms of splitting the two clusters. So single link clustering, on the other hand, is very sensitive to noise and outliers. Okay, and then it is kind of a characteristic of a single link clustering that it produces a long elongated clusters, because if you think about it, when you compare the distance between two clusters and then determine whether or not to merge the two clusters together, we're using the shortest distance between the two clusters. So one cluster can expand in one direction like this by merging the other clusters, because even if there's a bigger trend or pattern going on, single link clustering is going to simply just merge the closest cluster together, and because of that, it may produce a long elongated cluster. So when you don't have this kind of, let me go back to the previous slide. When you don't have this kind of a clear distinction between two clusters, when you use single link clustering, you're going to have the result that is not so desirable. So when you have some level of certainty, either from visualization or from a domain knowledge or whatever, when you have some certainty that the data has some clear boundary between the two, then single link clustering is the way to go. But if you have lots of noise, and if you don't have a full certainty that the measurement is clear and nice, then the chances you're going to have some weird clustering result as a result of using single link distance scheme. Okay. Now, the fact that we have the single link, which is the minimum, it is easy for us to think about the opposite situation. So instead of the minimum in the equation, what about we take the maximum? So that is what is called a complete link distance. So it's a totally different opposite situation. So here's a cluster formed by these 6 points. And then here's a cluster that is formed by 4 points over here. Now, the single link distance was basically to select the one that has the closest proximity. The complete link distance is we define the distance between two clusters by using the furthest pair possible. So in this diagram, perhaps this and this will define the furthest distance between two pairs, and that's what we define as a complete link distance. Now, in terms of merging, the values, obviously, the beginning is the same. We're going to find the distance matrix, by computing it. And then, we're going to find the one that has the largest value in the proximity matrix. And then we get to merge this two. But then, unlikely to, in contrast to the single link distance, where we have chosen the one that has the highest proximity. Sorry, not this one, this and this and this. In the complete link distance, we're going to actually keep the one that has the smallest proximity, okay? The ones that has the lowest proximity. And that's basically going to be the way that we compute the complete link clustering. So as a result of that, let's try just step by step, just to make sure that everyone kind of understand the process. So again, this 3x3 area is going to be kept as is, and that's going to be the 3x3 block after merging, which we didn't introduce any change. And then, the first two rows are going to be merged into one. And then, for the rest, we're going to select the ones that has the lowest value. So then, 0 0.1, 0 0.6, and 0 0.2 is going to be the value, right? Now, from the upper triangle, we're going to find the one that has the largest value, largest proximity. And that's the pair formed by point number 4 and point number 5. So that means we're going to merge these two columns together. And then when we do so, we're going to keep the ones that has smaller proximity, okay, as opposed to the larger proximity as in the single link cluster case. So, by repeating this, the resultant dendrogram is going to be a little bit different from the single link clustering. Now, the strengths of this is that, well, since this is kind of an opposite, you can kind of think of its strengths and the limitation in an opposite way than the single link clustering. So in case of single link clustering, when you had the noise in the middle, it didn't work very well in case of single link clustering. But in case of complete link clustering, it is less sensitive to the noise and not outliers like this. And then as a result of that, you can have more robust clustering result compared to single link clustering. Okay, so the biggest characteristic of a complete link clustering is that it is susceptible to noise, less susceptible to noise. Now, in contrast to single link clustering, though, when you have kind of an unbalanced data, you may end up clustering, this data distribution into something weird like this. So this is kind of a limitation of complete link clustering, which is kind of an opposite. In case of single link clustering, it did pretty well in, clustering, a small cluster and a large cluster. But in case of complete link clustering, it doesn't work anymore like that. So from this analysis, what do you think? You probably want to combine the pros and cons of single link and the complete link clustering. So instead of, you probably want to take the advantage of complete link clustering in terms of the sensitivity to noise or robustness to noise, but you want to take the advantage of a single link clustering in terms of the tendency of breaking the large clusters and merging them into small clusters, right? So that's exactly what people thought, and here's another scheme, which is called a group average distance. And the group average distance is basically the distance between the clusters defined as the average distance between all possible pairs. So for example, let's say you have a cluster formed by these 4 data points, and then a cluster formed by 3 data points like this. Now, what you do is to find all possible pairs like this, okay? And then you compute the distances among all possible pairs, and then simply take the average of the distance values, and that's going to be the distance between the 2 clusters. So the group average distance is sort of something in the middle between the single link distance and the complete link distance. Okay, so instead of taking the extreme, let's take something in between is the idea behind the group average distance. Now, it may sound a little scary because you need to take the average among all data points, but in reality, what really happens is you basically take the average value between the 2 rows. So, let's say again, the point 1 and point 2 are the closest one, and then when we merge them, in case of single link distance, we've selected simply the one that has the largest proximity, and then in case of complete link distance, we have simply selected the one that has the smallest proximity. In case of average link clustering, what we're going to do is to take the average between the 2 values. So 0.1 and 0.7, the average between the 2 is 0.4, and that's going to be the new value after merging the distance matrix. Again, similarly, 0.65 and 0.60, the average between the 2 is going to be 0.625, and that's going to be the new value for after merging. Same thing, 0.2 and 0.5, it's going to be 0.35, right, if you take the average, and that's going to be the new value after merging the distance matrix. So, those are the 3 kind of, really popular distance metrics between 2 clusters. So in case of hierarchical clustering, you have to define 2 things. First of all, you need to define which distance metric you're going to use to build the distance matrix. And for that, we're talking about point-to-point distance. So, options that you can select from includes the Euclidean distance or more generic Minkowski distance families. You could also think about the cosine distance and things like that, right? So you have to first decide which distance metric you're going to use to compute this distance matrix. The second thing you need to decide is the distance metric between two clusters, which is called the link. Okay, so which linkage scheme you're going to use is to be the second thing that needs to be determined. So are you going to use the single link distance? Are you going to use a complete link distance? Are you going to use the average link distance? So those two are kind of the parameters that you have to define in order to run hierarchical clustering. So like I said, average link clustering is sort of a compromise between single and a complete link. And as a result of that, it is pretty robust to noise and outliers. And then, it's also kind of, similar to the single link clustering when you have the two unbalanced clusters. It does a fairly good job in splitting this, these two things, as opposed to the complete link distance where, it ended up breaking the large cluster into, and then merge that section into the small cluster. So if you have no idea what to do, I think, my first choice would be average link clustering in many cases. Now, with that, we have covered pretty much everything about hierarchical clustering. Now, since we're talking about big data scenario, hierarchical clustering is actually very expensive. Because first of all, you need to compute the distance matrix, which is already kind of time consuming. So when you have a large, non-small data set, okay? So for a data set that has like few hundreds or a few thousands of data points, hierarchical clustering can be, fairly useful. But when you have a large data set, something larger than, a few thousand, then computing the hierarchical clustering can be really time consuming. And of course, as you've seen from the previous slide, we need to somehow carry this distance matrix all the time, right? And what it means is you need to have a memory space to, store this distance matrix throughout the iteration, which is, again, computationally not so beneficial. So as a matter of fact, in terms of the memory space requirement, we have n square order of space requirement just for storing the distance matrix. And in terms of the complexity and the speed of the calculation, it is n to the cube, okay? So in the previous discussion, we've seen that in big data scenario, even the linear complexity is not, okay, right? And then we kind of discussed some strategies to, break it down even further to make it faster than the linear complexity, right? If you recall. Now, what we're talking about in case of hierarchical clustering is we have an n to the n cube of complexity, which is totally out of the ballpark in terms of the computational complexity. So when it comes to the big data scenario, no one really wants to use hierarchical clustering, in fact. So, but then there are kind of dilemmas, right? In case of k-means clustering, since we're kind of taking the top-down approach where, we have some data distribution like this, and then, we had to somehow randomly initialize the averages, the means, and then somehow iteratively, kind of try to find the cluster. But then the nice thing about the hierarchical clustering was that, we could, in a bottom-up fashion, we could merge the closest pairs together and then start kind of growing the cluster into the final one. So that was kind of a nice thing about hierarchical clustering. So what we're going to discuss next is going to be how to actually kind of leverage the spirit of hierarchical clustering, but in a way that doesn't really hurt the computational speed. Okay, the things that we didn't like about k-means was that we had to specify k. We had to manually define k, whereas hierarchical clustering could automatically define that once you have the threshold value. And then second, the result of k-means clustering was kind of random, so it required a multiple execution, right? in order to have a robust clustering result. Whereas hierarchical clustering, it's not random at all. So once the distance metric and the linkage metric is defined, the result of hierarchical clustering is, is going to be the same. So hierarchical clustering is more robust, right, compared to k-means clustering. But the critical downside is that it's very, very, very expensive. So that leads us to the discussion of the clustering algorithms for big data. So let me pull up the next lecture slide. So now, given that we have some basic understanding of clustering algorithms for small data problems, now we're going to expand this to large data problems. Okay. So first of all, we're going to go back to the k-means clustering because we didn't really talk about how to make k-means clustering algorithm much more efficient. So the default k-means clustering algorithm is not going to be suitable for a big data scenario. Instead, you probably want to have something faster in terms of computational speed. So just as a recap from what we learned last time, the k-means algorithm begins with a user-specified value k, and that's the parameter defining the number of clusters. So let's say k equals to 2 is what the user has set. Now we randomly generate the means, and those are the ones that will represent a cluster. And then based on the initial mean, we're going to find the membership of the data points. So whichever is closer, okay, so from the perspective of this point over here, the orange mean is closer than the blue mean. So the membership of this point is going to be determined as orange. And then if you repeat this process, this is going to be the initial setup you're going to see. And then based on that, we update the mean. So among all the blue members, we're going to compute the average. And that's going to be determined somewhere over here. Same thing among all the orange members, we're going to determine we're going to compute the average of the orange point, and that's going to be somewhere over here. And using that, we're going to update the means. And then with the updated means, we change the membership. And then basically repeating this process over and over again is going to give you a nice clustering result of the data. Now, if you think about it, what's going to be the problem regarding the Lloyd's algorithm? So, there are two steps. One is update membership. And then the second thing is update mean. And then the Lloyd's algorithm is basically the repetition of these two steps until convergence, right? So I was going to, put you on in the breakout room to have a chance to discuss, what's going to be the issues regarding the Lloyd's algorithm when the number of data n is really large. But since we're kind of, well, I don't know. I think we're kind of running out of time a little bit. So maybe instead of going into the breakout rooms, if you guys have any ideas or thoughts, feel free to unmute yourself and speak up. Or alternatively, you can write in the chat. So what's going to happen when the n is large? What's going to happen to the Lloyd's algorithm when n is large? Let's consider this scenario over here. So we just computed the new mean. Okay, here. We just computed a new mean. Now you need to update the membership. And in order to update the membership, what you need to do is to visit all the data points. You need to visit all the data points and then compute the distance from each data point to all the means. So when you have n data samples and you have k means, what that means is for each of the data point, you need to compute the distance for k times. And since you have total n data points, you're going to need to compute a total n times k number of distance calculations, right? So again, when n is small and k is small, then you're good to go. But when n is large, then no matter how small k is, it might be a computational burden for when you compute the membership. The second thing is when you update the mean, again, in order to update the mean, you have to visit all the data points that belongs to a particular cluster. But then since we have a large n, each cluster is going to have a large number of members. And computing the mean is going to be, again, burdensome computationally, because simply having a large number is going to mean that you're going to need to compute the distance, many times. And because of that, the Lloyd's algorithm can be slowed down. Of course, compared to the other clustering algorithms, like, for example, in an extreme case, hierarchical clustering, k-means is still much faster than the other algorithms. But here we're talking about, speeding up at least a little bit, so that when you have a large number of n, still, the net gain of the speed is significantly faster. Right? That's kind of the idea over here. So regarding that, here's one formulation that you may want to consider, which is formulation of k-means clustering algorithm as a gradient descent problem. So if you recall, the goal of k-means clustering was to minimize this equation over here, where the mi are the ones that we want to find, right? And then x is essentially the data point, right? Now, instead of considering this in that heuristic of Lloyd's algorithm, here you can use the gradient descent algorithm. So in case you don't know what gradient descent is, the idea of gradient descent is to use the gradient of a function value. So let's say f is the function that you want to minimize. The gradient descent algorithm says, start from some initial condition x, and then update the initial condition x by using the gradient value. So some coefficient times the gradient of function f, okay, is going to give you an improved value, so a better value than the previous x. And then as you repeat this process over and over again, you're going to converge into an optimal solution. So that's what the gradient descent algorithm is about. So for those of you who have never heard about this, here's a good analogy. Suppose you're a nearsighted person, and we're going to just assume an extreme case. So you're extremely nearsighted, and you can only see things within around 6 feet of your periphery. So you're standing here, and then you can see only like a 6 feet boundary around you, and then anything beyond that is not visible. Okay. Then let's say you want to find the top of the mountain, so you want to climb up the mountain, but you're extremely nearsighted person. So what that means is you have no idea which direction the peak of the mountain is, right? So in that case, the best strategy for you to take is, you may want to palpate the surroundings. So you basically touch the points using your foot, and then by touching the points around you, by palpating the points around you, you can find the one that has the the highest increment from where you're standing. Okay, and then make one step towards that direction. And then now you're here standing in this new location, and then you palpate the 6 feet area around you, and then find the direction that gives you the greatest increment, right? And keep repeating this process. If you're lucky, you may end up at the top of the hill, and that's simply the gradient descent algorithm in a nutshell. So like I just said, here consider the mountain. Now we're seeing the mountain from the bird eye view, and then we're considering a steepest ascent algorithm. So steepest ascent, like I just said, is you're starting from one location, and then you look around, and then find the direction that gives you the steepest increment of the height. Okay, and then once you find that direction, you make one step towards that direction that gives you the steepest increment, and then repeat the same thing. From here, look around and find the direction that gives you the steepest increment, and then basically repeating that process is going to lead you to the peak of the mountain. Okay, so that's for maximization algorithm. For minimization, it's basically the opposite process. So instead of finding the steepest increment, you want to find the direction that gives you the steepest decrement of the height. And then if you follow that direction, each step, you're going to be converging to the gorge where the height is the minimum. So that's for the minimization problem. Now, mathematically speaking, the gradient of a function, so the function value the height of the mountain is indicative of the function value. And mathematically speaking, the gradient of the function, which is defined to be a vector. In case of 2D, this is what this gradient vector looks like. And basically this gives you the slope along the x-axis and the slope along the y-axis, right? So in a single variable calculus, when you have a function value respect to the domain x, right? If you compute the derivative of the function f with respect to the parameter value x, that gives you the slope of the function. So basically the gradient is kind of a 2D version of that, or an n-dimensional version of that, where the gradient gives you the vector that indicates the steepest direction of increase in function value. Okay, so in case of steepest descent, the strategy that I just described, if you write it down in a mathematical equation, what that means is here x is the position where you're standing at, and then you're going to follow the direction of the steepest increase, because the definition of the gradient gives you the direction of the steepest increase. So we're going to follow the direction of the gradient vector. And then when you do that, alpha is a parameter that determines the learning rate. So how aggressive or conservative are you going to make your move? So when alpha is small, then you're going to make a conservative move. When the alpha is big, you're going to make a more aggressive move. And then that's going to be my next position. So this is the steepest descent algorithm, and the steepest descent algorithm is simply this plus sign converted into negative sign. Okay. So with that, long story short, what's going to happen is the gradient of this, in fact, turns out to be this simple equation, because the definition of the objective function is quadratic. So it's pretty simple to find the gradient of that objective function. And then at the end of the day, you're going to realize that the gradient descent update of the means is essentially this, which is not too far from the Lloyd's algorithm, in fact. Okay. So here, what's happening over here, in this step is we basically find the gap between the current mean and the data points that belongs to that mean. So what that means is here is, my mean x, and then let's say, we have data points x, okay, that are members of the cluster defined by M. Now, x minus M is a vector connecting the mean with the data points. And by taking the summation, we're having an effect of taking the average, right? So, in fact, what this equation means is we're taking the average difference, okay, between mean and the individual data points. So there's going to be some average, right, that aggregates, all these differences. And that's going to be the direction where I'll be moving my mean. And it is easy to show that if you actually, split this summation, into like two individual summations. It is easy to show that this equation, in fact, is similar to the Lloyd's algorithm, where you compute the mean of the members x, and let's say that's the one, and then you're basically moving the current mean to the average of the members in x. And of course, we have the step length over here. So that's the difference between the Lloyd's algorithm and the gradient descent version of k-means. So instead of going directly to that mean, we multiply some coefficient or some parameter, so that we're making more conservative move than to go directly to the average of the members. So that is the gradient descent formulation of k-means, which is pretty similar to the Lloyd's algorithm. Now, if you think about this equation now, this is kind of a good news, because for the fact that we have the sigma like this, okay, means that you can compute a sort of a distributed average. In case you have a distributed computing clusters, instead of one single core to compute everything, you could actually compute the average in a distributed fashion. So the summation symbol is simply just adding a bunch of data, okay, and then you can group them, in whatever order, and then later on you can merge them together. It doesn't really matter. So, like this is something that we talked about at the very beginning of the semester. So when you have a task of adding, numbers from 1 to 100, it doesn't matter how you split the summation, right? You could split the summation into smaller chunks, give them to individual computing cores, and then, have them submit the numbers, the local summation, and then at the end, you could aggregate them together. Okay, so that was the concept of mappers and reducers, right? The mappers basically distribute the addition task, the summation task, to multiple cores, and then the reducers basically aggregate them together to produce the final number. So the fact that you could formulate the k-means clustering algorithm in this gradient descent formulation, where you have a sigma of the cluster points, you can simply parallelize the algorithm by distributing the computation to the multiple cores. Another nice thing about the gradient descent formulation is that you can make the gradient computation more stochastic. So instead of trying to compute an exact gradient, you can in fact compute a stochastic gradient. So instead of just going through the pseudocode, here's a more graphical, more visual illustration of what happens. So in order to compute the actual, rigorous exact gradient, you're going to need to go over the entire members of a cluster, and then, sum them up. And that's going to be the gradient value that is defined from the data set. Now, for the sake of computational speed, let's say we do some sloppy computation for the gradient. So let's say, a cluster has 1 million members, okay? What that means is you need to do 1 million times of summation in order to compute the exact gradient, right? But instead, let's say we're sampling only 1,000 batch of the members. And instead of taking the summation on the entire 1 million members, now you're doing the summation on only 1,000 members. In terms of the accuracy of the gradient computation, obviously there's going to be an error. So if the black arrow is the direction of the exact gradient, by taking that stochastic approximation of the gradient, you're going to have some sort of an error. Okay, so as a result of that, instead of converging directly to the local minima, you're going to end up spending a lot of time kind of going a detour, right, in the search space before to actually converge to the local minimum. But the idea of stochastic gradient is, well, let's, instead of trying to be perfect, let's just, leave with an imperfect calculation of the gradient for the sake of improving the computational speed. So here's kind of a hypothetical scenario. Let's say you're computing an exact gradient value, and because of that exact computation, each step of gradient computation takes about an hour, okay? Of course, you're taking the exact gradient, so your chance of converging to the local minima, I mean, in terms of the number of iterations that you would need to converge to the local minima, is going to be very small, right? Because you're taking the shortest path by following the gradient. So let's say in this hypothetical example, we have 6 steps, and each step takes about an hour of computation. And that means we have 6 hours of computation required in order to compute the exact gradient descent. On the other hand, in case of stochastic gradient descent, because of the inaccuracy in the gradient computation, let's say, instead of only 6 steps, let's say it takes more than, much more than 6 steps. So it doubles, for example, to 11 steps. But then by, avoiding the calculation of taking the summation over, for example, 1 million data points, and instead, taking the summation over only 1,000 data points, you can dramatically reduce the, the number of, the computational time for each iteration step. And in this hypothetical example, let's say, each iteration takes about 10 minutes. So while we're taking detour, okay, in terms of the total computational time, we can still save a great deal of time in doing the computation, while the solution that converges from the stochastic descent, the stochastic descent algorithm, is close enough to the exact gradient descent algorithm. So as a matter of fact, here's k-means clustering algorithm, sort of computed in a 2 different manner. So on the left-hand side, we have the k-means algorithm using the exact, gradient descent algorithm. And here's the result of K-means algorithm after convergence. Here's also a mini-batch K-means algorithm where we have the instead of exact gradient, we have the stochastic gradient, and then as a result of that, we have converged into this solution over here. I think the labels are kind of flipped. It's got to be actually the K-means, the exact K-means got to be take longer time, and then the mini-batch K-means takes a shorter time. But anyways, so there are two different methods that we use to compute the K-means algorithm. And then here, as you can see, the difference is only a very small number of points, right? So globally speaking, the sloppiness in computing the K-means clustering doesn't really hurt too much in terms of the final performance. Okay, whereas in terms of computational time, using the stochastic gradient saves a lot of time, compared to the exact K-means algorithm. So again, these are the small data examples still. There's not a lot of points over here. So the difference is only like, a few tens of milliseconds. But when you have a large data set, then, the computational speed can be dramatically different. Okay? So that's something to consider. So that's about K-means clustering in big data version. Now what we're going to do is, in fact, on Thursday, we're going to talk about kind of a big data version of hierarchical clustering. It's not exactly hierarchical clustering, but we're going to approach to this problem from the similar spirit. In case of K-means clustering, the clustering result is not always desirable, because K-means is kind of top-down approach where it tries to partition the data distribution into kind of an equally spaced partitions, whereas hierarchical clustering gives you a result where you build the clusters bottom up. So you start merging individual data points based on the proximity, and then you kind of grow this cluster based on how close the data points are. So compared to this top-down K-means approach, hierarchical clustering performs much better in case where you have highly nonlinear distribution. So we're going to talk about that. The biggest problem of hierarchical clustering was that the computational time was just prohibitively expensive. So in fact, we're going to introduce a new algorithm called dbScan, which uses a density-based clustering, so similar spirit to hierarchical clustering. So that's something we're going to talk about on Thursday. And then hopefully, if the time allows, on Thursday, we're going to also see how the clustering algorithms are implemented in Spark. And then we're going to have a chance to practice a little bit in terms of how to use clustering algorithms in Spark. So that's kind of the plan before Thanksgiving. So thank you very much, guys.